distance between a point and a straight line. This is a little bit tricky, but I think once you got the idea, it's quite easy to do the calculation steps. So let's say we have a straight line here. This is my pen, straight line, and we have the ball head of a needle. So this is a point, and the way how to calculate now the distance. Usually the exercise always says the smallest distance, since of course there are a lot of distances. You could, for example, take some distance like this to the straight line, like this, right? So you can choose actually, but the smallest, there's only one smallest distance, which is, maybe you can already see it, which is of course orthogonal to the straight line. So we know it has to be some sort of normal vector to the straight line, which goes through our point. And this is how it works in principle. And this normal vector, I'll use auxiliary plane in the calculation, because it's when you use this, it's quite easy. And then you need to you need to find the intersection point between the normal vector and the straight line. And then you have 2 points. When you have 2 points, you can calculate, right? 2 needles, 2 points. When you have 2 points, you can calculate the connecting vector, and then you can calculate the amount of the connecting vector, and then of course you end up with the distance. So in principle it's not too difficult, but of course the calculation is a little bit tricky, and that's why practice helps, and I'll show how it works in the following video. How to calculate the distance between a point and a straight line. This is a little bit tricky, but I'm going to show you how it works with an example, which is the following. So we have a straight line G with a point -5, -3, -1 plus U times 3 -4 and 9, and I call this vector, this is the directional vector, V, and this is our point, and I say the vector according to this point, our support vector, I call L. We need that for later. And we have a point, which is, let's say, P, and the vector according to P is, we say also vector P. But don't be confused, one is the point and the other one is the according vector. -4, -2, and 1. And not to forget, U is element R. It's not a vector, it's like just a number. And the task now is the exercise calculate the smallest distance. And how does it work in general? I mean, just imagine you have a straight line and you have some sort of point, let's say here, and you want to know the smallest distance. There are a lot of distances you could calculate, but of course the smallest distance is like this one, right? And this distance, how can we, what can we say about it? It's 90 degrees to the straight line, right? So maybe I can draw a picture for you so that it's easier to understand. So we have our straight line here, and we have our point, which we said we call P, and the according vector we call P for this point, right? And we want to calculate now the smallest distance between our straight line G and the point. And I already said this is, come on, here. We can say that there's another straight line, which is 90 degrees to our first straight line, and we can say, okay, when we put this straight line right through P, then we have an intersection point with G, and now the closest, the smallest distance is this one. right? It's in between the intersection point and P, right? So it's actually, for the principle is not too difficult, but the calculation is a little bit tricky. You have to do it several times, I think. You need practice. But then once you got it, then you got it, right? It's feasible. So I just talked about the principle in general, but major step I didn't talk about yet is we have to introduce an auxiliary plane, which is with a straight line as a normal vector, and we say, maybe I can show you, this is our auxiliary plane, right? And it has the straight line G as normal vector, so we can say, okay, this is our plane, and now we say, okay, we don't know how to adjust it, and we say, okay, we put it right through P, and then we can identify this point, which is the intersection point between our auxiliary plane and the straight line. Then when we have this point, we can build a connecting vector between this point and P, then calculate the amount, and the amount then is the distance. So I hope the demonstration helps you a little bit, but I know maybe if it's the first time you're hearing the principle, it's maybe a little bit confusing, but maybe it gets better with the calculations. So I'm just going to show you how it works. So step 0, we have to find out, or we have to talk about something which is essential, and here I'm just going to say, okay, my point P is not element of G, because if it were element of G, I couldn't calculate the distance. Of course, the distance would be 0 and the entire calculation wouldn't make any sense. So in this case, I want to show you how to calculate the real distance, which is not 0. So I say P is not an element of G. But usually if you don't have this assumption given, or you don't know, then you should just insert, you should check whether the point is part of G or not. I also have a video on that if you want to know how it works. This is quite easy. So we say in this case we can just assume that P is not element of G. Now, the auxiliary plane. I call it E, and in our case E is actually, with the auxiliary plane we can already solve several of the steps. And with the auxiliary plane, we solve already, we can create the plane. We can let it intersect with P, and also we will directly get the point here, which let's say we call S. So that's what we can find out, and with a point, then we can calculate the connecting vector, and then we can calculate the amount of the connecting vector. So the auxiliary plane, therefore, is V times X, which is V times P. So this is a formula you should keep in mind, and the rest is quite straightforward then if you know the formula. And what is X exactly? V, we know. I already told you that's our directional vector of the straight line, but what is X? And we directly insert the straight line. That's how it works. That's why we can already calculate several steps with the auxiliary plane. So we directly insert our straight line and calculate the intersecting point, which is S. And therefore we write our straight line as a general point, which then looks following. So I just take all the 3 components each and write it down. So minus 5 plus 3u. X2 is minus 3 minus 4u. X3 is minus 1 plus 9u. So now we have just written down our straight line as a general point, and then we can insert our general point together with the directional vector, together with our point, all in our auxiliary plane equation, and we obtain directly a value u, which we can then therefore insert in our straight line. Then we obtain the point S, and then it's quite easy, just calculate the connecting vector and the amount of the connecting vector. So now it gets a little bit more complicated, but we can do it. It's just math. You know, you have to practice it, and once you can calculate and you don't make any mistakes in general math, then it's quite easy again. So we just calculate component wise. So v1 x1 plus v2 x2 plus v3 x3. We need a lot of space there. Equals v1 p1 plus v2 p2 plus v3 p3. Now we just have to insert our values. So v1 we already have, since that's our directional vector. So that's 3 times, now x1 minus 5 plus 3u plus, or in this case, minus 4 times minus 3 minus 4u plus 9 times minus 1 plus 9u equals v1 p1. So 3 times minus 4 is minus 12. v2 p2 minus 4 times minus 2 is plus 8. v3 p3 plus 9. So we have to multiply the brackets. So we end up with minus 15 plus 9u plus 12 plus 16u minus 9 plus 81u equals. So we have minus 12 plus 8 is minus 4. 9 minus 4 is 5. So on the left side we have minus 15 plus, or minus 15 plus 12 is minus 3. Minus 3 minus 9 is minus 12. 9u plus 81u, we end up with 90u. 90u plus 16u are 106u. Right? So actually not too difficult. Then we say plus 12. 106u equals 17 divided by 106. U is 17/106. And this may not look very beautiful here on the right side, but it is a value, which is okay. And we can insert it now in our straight line. That's what we are going to do. So, straight line looks the following: equals minus 5 minus 3 minus 1 plus 17 divided by 106 times 3 minus 4 and 9. Which is, okay, in this case it doesn't make too much sense if you have a calculator to do it in the brain. So what we are going to do is we just use a calculator to make it a little bit more easy, since the number is not too nice in this case, unfortunately. So we have minus 5 plus 17 divided by 106 times 3 is minus 4.5 something. And we save that in A. So what else? We have minus 3 plus 17 divided by 106 times minus 4, which is minus 3.6 something, which we save at B, store at B. And then we have minus 1 plus 17 divided by 106 times 9, not 94, 9, that looks good, which is 0.4, which we save at C. And if you're not sure whether every storage works, actually, you can just have a check, just to be sure. and everything looks fine. We have all our values now stored in the calculator, which is good, so I don't have to type all the things again, and it's very accurate. It's as accurate as the calculator can do it. And then we say, okay, this point, which we called S earlier, so we say actually it's the vector S, so that we can calculate a connecting vector. Or we can also say maybe P, something S, point S, vector S. You have to be a little bit careful with that. And then we can calculate the connecting vector, which we say, let's say SP. It doesn't really matter because we calculate the amounts. Anyway, if you calculate SP or PS, doesn't make any difference now. So we calculate. We need first P minus S. Minus 4, minus 2, and 1. Minus S, when we just said minus 4.5, minus 3.6, and 0.4. And then we can calculate it. It's not too easy at this point, right? We have all the information, or all these values in our calculator. The other ones are just quite easy, so we just have to calculate it. Minus A, which is 0.5 something. And we store it in D. Store D. Then we calculate minus 2 minus B, which is 1.6 something. And we store it in E. Then what else? We have 1 minus C, which is 0.6 if we round, 0.5 something, which we store in F. And then what we are going to do is the final step. We just need to calculate distance, which is the amount of this connecting vector SP. So we say we take 0.5 squared plus 1.6 squared plus 0.6 squared square root, and then we end up with the amount. So since we have stored all our values, we can just check, because sometimes it can happen that you forget about storing a value and then you have an old value in one of those storing spaces, and then you calculate it actually wrong, although it's quite easy. You could easily check your values. So we just check, okay, this looks good, D, E looks good, and F looks, well, I didn't store it, C, so we just need to calculate again. 1 minus C we said, we store it in F, so now it looks good. F, we have our value. Then it's quite easy, so we just say square root of, not A, but we had D, E, F, D plus E plus F, when we forget the square, squared, again, shift, insert, squared plus F squared, DEF squared, and then we end up with, yes, 1.8093 something. And when you need this value for another calculation, you can also store it again, of course, and then continue. But in this case, we are finished. We have found our distance, the smallest distance between our 2 points. And as you've seen, it's not too difficult in this case, although we have one strange one, not so nice number in between, but it doesn't really matter. You just take the number, and if you have a calculator, you don't have to worry. You can put everything in your calculator and it can calculate for you, which is quite nice. So just to repeat the principle, so as we see, we have here our straight line G, then we have our point here, and we said we need an auxiliary plane, we need something so that we can say, okay, this is the smallest distance, which is 90 degrees to G. So we said we do it with the auxiliary plane, and we put in P, and at the same time we insert already G to calculate the intersection point, which is S, which we obtained finally. So we got U out of the auxiliary plane, then we calculated S by putting U back in the straight line, and then we calculated the connecting vector between S and P and just took the amount of this connecting vectors. Also, we found out that it doesn't really matter if you take SP or PS, since we take the amount anyway, right? So one way you have this vector and the other way you have this vector, but the amount finally is the same, so it doesn't really matter if SP or PS. Amount you calculate by squaring all your single elements and take the square root again, and then you end up with the amount. So this is how it works, distance between point and straight line. Thanks for watching. Practice makes perfect. Further exercises with solutions you can find on my website, which is www.worksheeps.com.